All right, what causes buoyancy? Why do things float? Well, we know that if they are less dense than water, they float. So we'll just write that down. We'll look at why. So water has a density of 1 gram per milliliter, or 1 kilogram per liter. So I think it's 1,000 kilograms per meter cubed is another way to write its density. So anything less than that's going to float, but why? What is it that makes that buoyant force on an object when you try to put it in a fluid? Well, first thing you got to know is there's buoyant force on objects in the air too. Any gas or liquid is a fluid. They exert pressure, and we've talked about how the pressure at a depth is equal to density of the fluid times gravity times however deep you are in the fluid. Density, gravity, height. So based on that, if you go underwater and you're standing here, the pressure is greater here and the pressure is lower here, right? If you decide to stand on your head, now the pressure would be greater on your head and lower on your feet. Well, that difference in pressure between the bottom of you and the top of you applies a force. So if you remember the general formula for pressure, it's force divided by area. So the force that it applies, the force of buoyancy, is equal to pressure difference times area. All right, so what is the pressure difference? Well, here we are, we'll call it H1 deep. And here, we'll call that H2 deep. So the force of buoyancy on this person is going to be PGH1 minus PGH2. That's the difference in pressure between the top and bottom of them times their area. Right, well, what is their area? Well, the area of anything, let's just, draw a little cube here. So its area is going to be its volume divided by its height. All right, well, I could clean this PGH1 minus PGH2 up and say PG change in H. Okay, and really, the difference between here and here is your change in H. So really, volume divided by change in H is what I want to put in for area. So I'm going to take PG change in H times volume divided by change in H. So look at that, it cancels. So it doesn't depend on your height at all. Really, the force of buoyancy is the density of the fluid times gravity times volume. Density of fluid times gravity times volume. So the more volume you have submerged in the fluid, the more buoyant force. If you're not in the fluid, you don't have any buoyant force. Okay, what do I mean when I say submerged? Well, here is some air, that's a fluid, right? I'm not there right now, the air is there. But now if I jump in here, splash, now there's a Mr. Dewey here, and that air is gone, right? So I displaced the air. I am submerged in air because I have displaced air. If I were to weigh that box of air that I just displaced, the weight of that air is actually how much buoyant force. Let me show you that from this formula. So PVG, why is that weight? Well, because if density is mass divided by volume, and it is, then volume is mass divided by density. So if I'm talking about the air that I'm in, I would take density times gravity times mass divided by density. Oh, density cancels, so it's just mass times gravity. So it is the weight, it's not my weight, it's the weight of the air that I displaced. If it's water, it's the weight of the water that I displaced. So density of the fluid matters. It determines how much weight you can displace. So if I'm talking about this little mass right here, if I put this in a very dense fluid, this mass, any sinking object can displace its volume. This mass could displace a lot of weight. If I put it in a not very dense fluid like air, which only weighs like something small like a kilogram per meter cubed, it can't displace very much weight of air because the fluid isn't very dense. So the buoyant force, this is probably the most important sentence here. The buoyant force equals the weight of the fluid displaced. The buoyant force equals the weight of the fluid displaced. So we talked about how less dense things float and more dense sink. Well, what's happening then? Well, let's say I set something on water and it's a wood block, so we're expecting it to float. When it's sitting on water, it starts to go in and it displaces a little bit. So water level comes up. Now, if we were to weigh that displaced water, if it weighs as much as the block does, then the force of buoyancy pushing up equals the force of weight pushing down, and this object's not going to move anymore because it's in equilibrium. The forces are balanced. There's as much pushing up as pushing down. All right, but what if this thing is real heavy? It's not wood. It's like lead. Well, now it weighs this much. Well, that's not enough buoyancy. So we're going to sink a little more, so the water level is going to come up. All right, well, now this is the weight of the fluid displaced. A little more buoyancy. But still not enough. So we're going to sink a little more. And we have more buoyancy. But it's still not equal to the weight. All right, at this point, we've ran out of volume. The best we can do is our volume. You can't displace more than your volume. You can only take up the space you take up. So this thing's going to go all the way to the bottom. Okay, so now here it is, sitting here on the bottom. Water levels come up by an amount exactly equal to its volume. And now that it's sitting on the bottom, this is where a lot of people forget that it still has weight and it still has buoyancy. And the buoyancy still doesn't equal its weight, but the bottom pushes up with some normal force. I think the weight was bigger than that, to balance it out. So between the normal force and the buoyancy, we've balanced out the weight of the object. So sinking objects actually have their maximum buoyancy for their particular volume because they've displaced their full volume. So if you ever were to look at two objects, let's say you had an object like this and same exact volume object made of wood, and you put them both in water and this one's sitting on the bottom and the wood's floating, you might think the wood has more buoyancy. But really, this has more buoyancy because it's used its full volume. It still didn't float because it has way more weight, but it does have more buoyancy. And the wood would be floating because its buoyancy is greater than its weight. So the buoyant force is equal to the weight of the fluid displaced. Right? What does that mean for things underwater then? Well, it means that if you went to pick this up underwater, it would weigh less. You only need to apply this normal force worth of force. So let's say that the volume of this object is, let's make it 10 milliliters, okay? And let's say that, we're not going to use weight, we'll use mass. Let's say that it's 20 grams. Okay, if I lift that object out of water, it's 20 grams to lift it. But now, when I put it in the water, it displaces 10 milliliters worth of water. Well, what is the weight of the fluid displaced? Well, 10 milliliters is 10 grams. So that means that there is something pushing up, reducing it by 10 grams. And so now, if I go to lift it underwater, it only feels like it weighs 10 grams, not 20. But the second I get it back out of the water, it's back to being 20. Okay, now really the mass didn't change because it has the same amount of matter. The weight didn't change, but it feels lighter underwater because there's a second force helping you, buoyant force. So sinking things have a buoyant force, floating things have a buoyant force. So here's just a few general rules that you got to know about buoyancy. We'll do a lot more practice with it. One is the force of buoyancy, I've already said, is PVG, which is density of the fluid. The volume displaced, which for a sinking object, let's write down that sinking objects displace their full volume. And finally, times by gravity, 9.8. Right, that way it turns into newtons. So it's not just like the reduced mass in grams, but it's really a force in newtons. Okay, sometimes we'll just look at the reduced mass in grams too. I'll show you an example of that. But really the force up is in newtons if we want to measure it technically. So we use PVG. Remember, this is about the fluid, not the object that's in there. If you're in a more dense fluid, you're going to be able to get a more buoyant force. Okay. Finally, floating objects displace their weight. Why do they displace their weight? Because they go in and they push water up, and once it equals their weight, they don't have any reason to push any more water up because they're in equilibrium. So they're not going to levitate off the surface of the fluid or something like that, because as soon as they would get pushed up to come out of the fluid, then they'd have less buoyant force. They just find this equilibrium where they just are just in the fluid just enough to float. All right, here you can notice my mass is 82.4 kilograms. Then as I put my fingers in the water, there's a force up on my fingers, which is what makes the scale go out of balance. And I have to bring it back into balance there. That force up on my fingers is the equal and opposite reaction force that pushes the containers down. You can really see that force up on me because now my mass is down to 82.1. Right, similar experiment now with a mass being submerged in water, and you can see that it was 1,600 and something grams, and as I put it in water, immediately that side goes down. Again, you probably wouldn't think it would because it's like submerged in water, but it goes down because there's a buoyant force up and there has to be an equal force pushing the beaker down. So I have to bring the double pan balance back in, and it takes 26.6 grams to get it back into balance. All right, so then once I get it back into balance, if we check out the electronic balance, you're going to notice that the electronic balance is not reading as much as what it used to be reading. It's going to be reading like 1,590 something, 1,592.8 grams. So that reduction in mass was exactly equal to the buoyant force up. This contraption here is showing that when something is spinning, the water goes to the outside because of its inertia. And since there's more pressure on the outside, the bobbers actually float to the inside. So not all buoyancy is always directed upward. In this case, these bobbers are floating in. Here I have a Cartesian diver. The way this works is you have a container that floats because there's air trapped in it. But when I squeeze it, I'm putting an external pressure on it, which compresses the air in the container. So if you look at that container, see how the air is smaller than what it used to be? That compressed air now does not have enough volume to make the object float. It can't displace enough. Right? This is a situation where a balloon is being held underwater by a mass. And then I have a second situation where a balloon is supporting a mass above the water. Right, finally, I am showing you how to find the amount of weight that something could hold. It can really hold additional weight until it runs out of volume. So as you add more and more weights, you can see that it's sitting lower and lower in water, and the water level's coming up. Once it's displaced all of its volume, if there is still more mass in the boat and it's ran out of volume, then it's going to sink. So I can only add a few more masses before I've displaced all of the volume of the boat. So you can see we're getting really close to the edge of the water level, and there it sinks. All right, so now the mass of the boat with all that weight in there, this looks like 6,960 grams, and then if I dump the weight out, I can't read it, but 1,364 grams. So you can tell that that additional weight was how much additional I could support with my volume. So the last thing I'd like you to do for today's video is go back and look at those two pictures where the balloon was both held underwater and floating on top of the water with the weight, and see if you could draw free body diagrams for those situations, because we'll be talking about them tomorrow.